Well, we're making some good progress here, and we are pretty much able to compute the transforms that we need, and we're also able to build up functions if we need them with unit step functions, um, but we haven't talked much about how to compute inverse transforms. And the reason that matters is when we solve a differential equation, we start with the original equation, we transform everything, do some algebra work on it, and then we need to transform back. And that step of transforming back is what actually gives us the solution to our ODE. So we need this skill. How do you find the inverse transform of something like this? Well, if you have just a fraction like this, it's typically going to fall into one of two categories. The first possibility is you might be able to factor this denominator here and then split this up into some simpler fractions. But if you try that on this one right here, you'll find out that it does not factor. So what do you do then? Well, the answer is we can just focus in on this rational function for now. And say, well, what we can do in that case is to complete the square. So what we want to do is look at this s squared plus 2s plus 401 and say, well, if we just change that a little bit, we can make that a perfect square. S squared plus, you take that middle coefficient 2, divide by 1, and then square it. So 2 divided by, I said that wrong. Take the middle coefficient, divide by 2, and then square it. So the middle coefficient is 2, divided by 2 is 1, and square it is 1, so I need a 1 there. Now I can't just go throwing ones in unless I take them back out. So I added a 1, therefore I'm going to subtract a 1, and then I'm going to write down that last term there, 400, and now you're starting to get some insight into where that 401 came from. This is s plus 1 all squared, and then I've got 400 left over, which happens to be 20 squared. Okay, now that means that this is the inverse transform of 40 over s plus 1 squared plus 20 squared. And now we're ready to go looking in our table of transforms. If you are looking for things with sums or difference of squares in the transform table, then you're looking for trigonometric or hyperbolic functions. So we've got, first of all, our particular problem has a plus in it, not a minus. So that means we're after a sine or a cosine form. And this one has a s in the numerator, and this one has a constant in the numerator. So we landed on this one here, and that comes from a sine of omega t. Now, in order to make this fit, f at t, let me just give that a name, f at t is the inverse transform of this. So f at t is inverse transform of, and everything is almost perfect just now. I just got one little change to make, and that is this. This number here and this number here need to match. So we had a 40, what we needed is a 20. Well, of course, there's no real problem with that. You just factor that 2 off, and then you could take that to the outside of the inverse transform. So this is simply 2 times the inverse transform of 20 over s plus 1 squared plus 20 squared. Now, if we didn't have the plus 1, if it were just s squared plus 20 squared, that would take us back to the sine of 20t. So this is going to involve the sine of 20 something, but it's not just t. And where it comes from, of course, is this shifting theorem that we've been working on. If you have s minus a here, well, then you just forget about the minus a for the time being to get that, which is what we've done, right? That's how far we've gotten. And then we say you need to multiply this by e to the at. So we're actually all set here. This is 20t, but then I need e to the at, and this is being shifted by 1, so e to the 1t. Another way of looking at that would be that we actually have a form here that's explicitly in the table. You set a equal to 1 and omega equal to 20, and you'd have exactly the form that we were working on, so that's e to the 1t sine 20t. So there is our inverse transform, and that's the first thing that could come up. If you have a quadratic denominator that does not factor, then you complete the square, muck around a little bit with the constants, and then apply your inverse transform formulas, and you'll have the transform. Now that's a good starting place, but they don't always come along quite so easily. So let's compute now another inverse transform, and this one is going to be a little bit more complex. So suppose we started, instead of starting with this one, suppose we started with this one here. Now, you can pretty much anticipate what's going to happen. We are going to probably split this up into a piece that has an s in the numerator, which will come back on the t-axis to a cosine form, and one that has a constant in the numerator that will come back to the sine. So this will be split up, but you don't want to probably do it just yet. And the reason is, now we already know from our work on the last one that when you complete the square on that denominator, you get this here, s plus 1 squared plus 20 squared. Okay, so far we're in pretty good shape. And now we'd say, well, this thing up in the numerator here, that is based on s. We really want it to be written in terms of s plus 1. Now, if you change that s to an s plus 1, 3s is good, but you added 3, right? So that would mean that you need then to subtract another 3. So minus 137 minus 3 is minus 140. And now we're ready to split this. This is the inverse transform of 3 times s plus 1 over s plus 1 squared plus 20 squared minus the inverse transform of 140 over s plus 1 squared plus 20 squared. Now, this just needs a little bit of touch up here, and the easiest way to do it is probably like this, to say, well, that 3 can come on the outside, and then s plus 1 over s plus 1 squared and 20 squared, we can apply our formula directly to that. So we have a s minus a minus 1 squared here, right? So we've got e to the minus t times this comes from the cosine form, cosine 20t, And this one, well, this is a little bit messy. What we'd really like is to have a 20 here. And you can get it. 140 divided by 20 is 7. So you factor a 7 out, and then you'd leave the 20 in and say the inverse transform of that. Well, that is going to come from a sine form, sine of 20t, but it has that shift of s minus a minus 1 times e to the minus t. So there is the transformation, inverse transform of that whole fraction. And I just noticed something before we leave this. Did you catch it? This I wrote as a +1. It really should be a minus, because that's s minus a minus 1. So that needs a negative sign on it. Otherwise, it's good. And there is the way to find inverse transforms of fractions, proper fractions, when the denominator is quadratic and it does not factor.